the future directions that I want to pursue while I'm a postdoc. And I decided to give an introduction to the CGC because maybe not all of us are very familiar with it. So today's presentation is somewhat conceptual, but of course, if you want to know more details, I'll be happy to address them. I think this topic is very timely because of the arrival of the EIC in a few years from now. And the CGC is a field that has grown significantly over the past few years, but it's only beginning to enter an era of precision computations. It's much behind other areas of physics, like, for example, computations in electroweak theory, which are known to higher loop accuracy. What you will find is that most of the color glass condensate observables are at leading order, and that might sound trivial, but in fact, because of multiple scattering, the computations already at leading order are not that simple. And the computations to next to leading order are much more challenging, but as a community, we're beginning to tackle them. And we are also beginning to make some connections with other frameworks, such as the TMD framework. So this is more or less the outline of my talk. So I would like to spend the first 15 minutes or so explaining what is the color glass condensate. And then I would like to discuss where it has been tested. I will very briefly mention observables at RIC, LHC, but my focus today is mostly on deep inelastic scattering, so I would lean on HERA and EIC. And as I said, I like to focus on the third part of my talk on precision computations, and I would like to give a brief overview of the status of the CGC, what observables have been computed next to leading order, and which ones are still underway. And at the end, I will provide an outlook of how I think the CGC is going to move forward within the next couple of years. So I would like to start with this picture. So this depicts, it's a cartoon of the proton. And as you see, when the proton is boosted to high energies for a given resolution of your probe, let's say you have DIS and you fix the virtuality of the process and you boost your proton, you're going to probe a smaller X physics. There is a simple relation that, of course, all of you know, which is that the X that you probe is Q squared over S, where S is the center of mass energy of the collision. So when the high energy limit is equivalent to the small x limit, and what you see is that this small x limit, you have a highly densely populated system of gluons, and the color glass condensate capitalizes on this idea of a highly dense system of gluons and builds an effective field theory to describe this domain. So this cartoon here, it shows you how the gluons are organized, how the phase space is organized as a function of X and the virtuality of the process Q squared. Or it can be also the transverse momentum of the jet, but let's keep it simple as virtuality. And what you see is that there is a so-called saturation scale, which depends on X and delineates this boundary. And this scale more or less tells you the transition between linear evolution and nonlinear evolution. So linear evolution, you can think as the splitting of the population of gluons, but there is also an effect which is expected to happen at high densities, which is the recombination. And when both effects balance each other, you obtain this saturated regime. And what delineates that transition between linear and nonlinear physics is the saturation scale QS, which grows as you go to smaller x, which means that it grows when you go to high energies. And not only it grows with energy, but it also grows with the nuclear species. It scales with the species that you have. So if you have a gold ion instead of a proton DIS, then this saturation scale increases, and you expect the nonlinear physics to kick in faster. And we want this saturation scale to be non-perturbative so that the calculations are reliable. So at large X, this saturation scale here is in a domain which is non-perturbative, and we have more difficulty to make computations, reliable computations in this regime. So the ideal scenario for this framework of the CGC is to go to high energies and to go to very dense nuclear systems. So if you open one of these CGC papers, you will see some terminology. And if you're not familiar with this terminology, you can get a little bit lost. So let me explain some of the things that you will see often in these papers. So as I said, this is an effective field theory. And what we do is we integrate out the large X degrees of freedom of the proton or the nucleus. And this process of integrating out these degrees of freedom, these are replaced by sources that travel along the licon. So these are color sources which form a current that travels along the licon. And these color sources induce a background field which characterizes the small x physics. And a little bit more formally, you can see it in this expression, which is something that you will see in CGC papers, this so-called double average. So as I said, there is a separation of degrees of freedom in which these are integrated out. And the way they speak to the small x physics is that these guys are gonna be sources. These rows, these sources, which will speak to the gauge fields which characterize these small x partons. There will be a scale which tells you what you consider as gauge field and what as sources. And of course, the observables should be independent of this scale, and there will be a renormalization group equation that tells you how to move this scale so that the observable is actually independent of this fictitious, scale which delineates these two kinds of degrees of freedom. But so yes, you will see this double average. So for a fixed set of sources, for a which represent these degrees of freedoms that have been integrated out, you solve the path integral associated and you compute the observable that you want. And then you average over different configuration of these sources. And these configurations of sources will be encoded in this W, is the gauge invariant weight functional, whose information is non-perturbative. Nonetheless, its evolution with this scale is perturbative and will be given by the so-called BK Jim-Wolk equations. And I will get there in a bit to explain in more detail how that comes up. But at leading order, this path integral will be dominated by the classical solution, which is a solution to these sources. So it's a solution to classical Yang-Mills equations to these sources. Okay? So at leading order, you will see that any observable can be computed by finding the classical solution in the presence of these sources, and then to make sure that the result is gauge invariant, you average over this weight functional, which, as I said, it contains a non-perturbative physics and has to be constrained by data in some way. By the way, if you have any question, please, I encourage you to interrupt me at any time if there is anything that is not clear or if I'm going too fast. I know that for some of you, this is very trivial and simple, but please interrupt me nonetheless if anything is not clear. And you can find much more details and information in this review. Okay. Now, another thing you will see a lot is these Wilson lines, and you will see things like multiple scattering, and you will read things about shockwave. And so what does this mean? So now we want to probe this physics. We want to probe these small X partons. So what you can do, the simplest thing you can do is you can send, let's say, a quark. And when you send that quark, it's going to multiply scatter from the background field, from this background field. Okay, which is to lowest order is just a classical solution. Why a multiple scattering and why not just a single scattering? Because at the CGC, we assume that this background field is of order 1 over the coupling, so it's a strong, strong overpopulated field. And so when you add a gluon, of course, you will have a coupling associated with it. But since it comes with this, so you, for each gluon attachment, you will have something like this. But of course, this is going to be order 1 if your the strength of this gauge field is order 1 over G. So you have to do a resummation, and this is precisely the multiple scattering. So you consider 1 scattering, 2 scattering, 3 scattering, and so forth. And you will see these kind of diagrams which represent precisely this multiple scattering of the quark with the background field of this nucleus, small X background field. And there is an effective vertex for that expression, whose precise form I will not show you here right now, but it will contain these Wilson lines, and these Wilson lines encode this multiple scattering within the so-called iconal approximation. And what the iconal approximation means is that the transverse location of this quark does not change. And it doesn't change because this interaction is like a shock wave. At high energies, the nucleus is going to be highly Lorentz contracted, and the interaction is going to be very fast. And the other way you can think of this Wilson line is as a color rotation. It's like a Bohm-Aharonov effect, but for QCD. So it's a non-abelian Bohm-Aharonov effect. And as you can see, what enters here is this gauge field. Okay, and in the CGC, observables will be expressed as a convolution of a string of Wilson lines or derivative of Wilson lines with factors that can be computed perturbatively. Okay, so you will have your observables will have this form, which with different Wilson lines. By the way, you can also scatter, of course, gluons. Now you will have a Wilson line, but not in this fundamental representation, but in the adjoint representation. And so you can also have Wilson lines in the adjoint representation for the observable that you have. But you get the idea. The idea is that you will have your cross sections or your amplitudes will be convolutions of perturbatively calculable factors with these Wilson lines. And oops, I don't know what happened. Just give me a second. I'm sorry. Don't know what happened to the.
Oh, it's okay. You have to reshare a screen.
Yes, just let me find. Just give me a minute so I can do this correctly. Okay. Okay, yeah, I'm sorry about that. I don't know what happened. So yeah, I was here. So yes, you will see these Wilson lines. Your observables will be expressed as products of these objects. And now let me give you an example. Let me give you 2 examples, in fact, to show you the universality of the color glass condensate. It can be used, it has been used for heavy ion collisions, it has been used for DIS, for proton nucleus collisions. As long as you probe small x physics, small x partons, this framework has been employed. And let me give you two examples. So on the left, you see semi-inclusive hadron production in proton nucleus collisions, and on the right you see DIS. Okay, so here is just the virtual photon that is exchanged in the deep inelastic scattering. And what you find out is that both of these processes are sensitive to the dipole. Okay, and the way you can understand that is that, for example, in this case, in the single inclusive hadron production, you have in the forward direction, and which what I mean by forward is in the direction of the proton, you can treat the proton as a dilute object, and you can use PDFs, and you will scatter a quark from that dilute object to this dense field, this dense background field, and the scattering will be encoded by these Wilson lines, which I showed you before. Okay, and you will have a Wilson line, and this is at the level of the amplitude. If you square this, you will have two Wilson lines, and that's why you have a dipole. Okay? And I will not give the precise expression now, but you can get the idea that you will have this dipole. Now you look at DIS in electron nucleus or electron proton collision. So the picture that that one has in mind is this so-called dipole picture. So you have your virtual photon splits into quark anti-quark, and that will interact with this shock wave. Okay, and you can take advantage of the so-called optical theorem, which relates the forward scattering amplitudes to the total cross-section, the total DIS cross-section, and so at the amplitude level, you have a dipole, and you have a dipole because you have a quark and an anti-quark, one Wilson line for the quark, and Wilson line in the Wilson conjugate Wilson line in the for the anti-quark. You have a dipole, and at the cross section, you also have a dipole by virtue of this optical theorem. Okay. And so even though you're looking at very different processes and at very different final states, you have the same dipole operator. And you can see that it's decently described. Both observables are decently described. So here, one can study, for example, the KT distribution of the produced hadron at different rapidities. And here one can study the energy evolution of the total cross-section, or how it depends on the virtuality of the process. And typically what one does is one constrains this operator by looking at Hera data, so PA, and then one looks at observables like this. One tries to make predictions for what is single hadron production, because the same dipole will be involved. The perturbative factors, of course, will be different, but those can be computed in perturbation theory. So the novel feature is this object. And just for you to get an idea of how this object looks like, so this is just a product of Wilson lines. And here I show you the so-called dipole amplitude. So it's 1 minus this product of Wilson lines. And you see it increases, and then it kind of saturates. And the region where this saturation happens is related to this so-called saturation scale. So it goes from this weak scattering regime to this strong scattering regime. And when that happens, that happens when this distance, the size of the dipole, or the distance between these Wilson lines, is of order 1/QS. And of course, this is just a very simple exercise. But if you have a larger QS, as in this red curve, this transition happens before than when you have a smaller QS, almost by definition of the QS. Okay. So what about, okay, so far I told you about the classical solution, which is a leading order. But where does the quantum evolution come from? So now you dress this dipole, for example, you dress it with gluons, you do your one loop correction, two loop corrections, and so forth. And what you will find is that, of course, these corrections are going to come with alpha S, but a part of that corrections is going to be enhanced. It's going to be logarithmically enhanced. And that enhancement depends on what you set your scale to be, and what is the scale at which you are looking at the physics. So if you look at the physics at some very small scale, you should have you have to renormalize this. So what you have to do is you should have integrated out these degrees of freedom, and you can show precisely that these corrections, if you go to perturbation theory and you calculate these logarithmically enhanced corrections, which are so-called these energy logs or rapidity logs, they can be re-expressed as an evolution in the weight functional describing the sources. Okay, because now physically what happens is that by moving this scale, you are integrating out also these degrees of freedom. So all of these are sources now. And that's precisely what this BK-Jim-Walk resummation does. It performs that renormalization of this scale. There would be a part, when you, process by process, when you compute it, there will be a part that is not enhanced by these energy logarithms, and that will be the truly alpha S suppressed, truly NLO correction, but that will be process by process. But so far, for the observables that have been computed, you always find that these pieces that are logarithmically enhanced with the energy logarithms obey this so-called small x BK-Jim-Walk resummation. So, okay, that has been some kind of theory review, but where has it been tested? So the CGC has been confronted in the different experiments, like Hera data, for example, here is shown this beautiful geometric scaling. So the total DAS cross-section should depend on X and on Q squared. But in fact, what the CGC predicts is that there is a scaling. It depends on also if you, this tau variable that is plotted here, you probably have seen this Q over QS, or maybe it's backwards. And so there is this scaling. So all the data falls within this, line here. It has also been used for nuclear modification factors in the hadron production, in forward hadron production, where it was observed this kind of Cronin peak, which then washes out as you go to forward rapidities. And it has also been tested with dihadron suppression. So there is a suppression of this back-to-back peak when you go from more dense collisions. So here you see proton-proton collisions, and here you see proton-aluminum is a little bit more suppressed. So this is a dihadron back-to-back. So the angle between the dihadrons, this distribution is suppressed. I should definitely mention that all of these observables, or most of these observables, have other competing mechanisms which lead to the same kind of physics. So none of these observables is truly proof or evidence or clear evidence of saturation. We have to work harder because there are other physical mechanisms which lead to these kind of signals. So this is kind of what we try to do in the CGC, is try to obtain observables which are hopefully clear signals of saturation and whose other competing mechanisms can be distinguished from. But a very important requirement for this is to have precise results, to do higher loop computations. But as I said, the CGC is beginning to go in this direction of high precision computations. So now let me tell you a little bit more about how the CGC applications for the electron-ion collider. Okay? And a natural point to start is with structure functions. And so what is shown here based on this paper is this longitudinal structure function for the proton and for gold. And what it shows you here is the difference between the saturated model, a model that includes gluon saturation, and one that doesn't. And you see that there is deviations which grow as you go to a smaller x, which is what you expect. You go to smaller x, you would expect saturation to be more important. And as you go to lower virtualities, so if you go, if you have a very fine probe, if you have high resolution, then you're not going to be sensitive to this dense regime. You're going to be more sensitive to the dilute regime. So you have to go in this kind of corner. And you see that these are enhanced when you go to nuclear collisions. And the reason it's enhanced is because, as I said, this saturation scale, which tells you the transition between linear and nonlinear physics, also grows not only with energy, but with the nuclear species. Okay. So the question is, will these kind of differences manifest at colliders? Okay. It seems like the differences are huge. So why can we observe them at colliders? So the reason is the following. For structure functions, there is also contamination, if you wish, from from large dipoles. So in this picture that I showed you before of DIS, you have this virtual photon which splits into quark anti-quark, and then it interacts with this shock wave. But for moderate values of the virtuality of the process, or for moderate values of Q square, there could be large dipole contributions. So when this dipole gets very large, and those are not reliable perturbatively. Okay, so you may say, why don't you just go to larger Q square so that you constrain these dipoles? Well, if you go to larger Q square, then you won't be much sensitive to saturation, right? So you have to play this kind of game in which you have to probe scales which are, so maybe let me write it down. So this is a little bit schematic, but you want to probe scales. So let me work in coordinate space, which are, this is the resolution of your probe. And you want this resolution to be not much larger than 1 over lambda QCD, because you get into the non-perturbative regime, but also not much larger than 1 over QS, because if you get to very small scales, you're not in the dense regime anymore. And at the energies of Hera, the differences between these two is not too large. So this window is very small. So the contribution from gluon saturation is expected to be small. And the way that manifests is, for example, in these plots. So in these plots, IPSAT is a model that includes gluon saturation. So these are fits of Hera data. They're reduced cross section with the IPSAT that includes gluon saturation, and the so-called IP non-SAT, which turns off this nonlinear physics. And they have both been fitted independently. Okay, and they both seem to give similar results for the fits. So the fits are equally good, which means that it's hard to really find clear evidence of gluon saturation at Hera. But notice that here the fits are independently done. If I do first the fit with IPSAT, and then I take those parameters and I turn off the nonlinear terms, there will be some differences, of course, right? But if you really want to distinguish the scenario in which gluon saturation is present or not, you have to do the fits independently. And as I said, the reason is because in this case, this structure function here has contribution from these large dipoles, even if you go to large Q square. Okay, so it's a little bit tricky. A way to go around this is to go and study charm structure functions, because the mass of the charm will provide a scale which suppresses these large dipoles. And but I think at HERA, and correct me if I'm wrong, the data for charm is not that great. So I hope that at the EIC one can constrain this data much better at small x for the structural functions. Okay. So how does the EIC can help you? So the EIC can help you because now, even though the energies are a little bit smaller than HERA, you have the enhancement of the nuclear enhancement of A. So you have larger saturation scale. So this window here grows a little bit. So we expect more sensitivity to saturation. And there are some ideas. So some ideas is to compute these structure functions within a saturated model constrained to HERA data and try to find some tension between those predictions and the predictions that you get from extrapolations of nuclear PDFs. And in this paper, that direction has been explored. And indeed, there seems to be some tension, but what is warned to the reader is that these nuclear structure functions are not well constrained at the small x. So perhaps if one does a refit of these nuclear structure functions, the tension might disappear, but I mean, this could be a way. Most of these studies focus on the light quark component of the structure functions, and I think that it could be interesting to look more deeply into the charm structure functions as they suffer less from these large dipoles and these non-perturbative contributions. There is also diffractive processes, and as I noticed that I'm speaking a little bit too much, so I have to move a little bit faster. But let me just say a few words for this slide. So diffractive processes are characterized by a rapidity gap, and this rapidity gap requires that the change is colorless. So in a way, they are sensitive to the square of Bloom distributions, and that's why they are considered to be excellent observable for saturation searches. And there are some differences of the expected behavior of, for example, ratio of diffractive structure functions to inclusive structure functions, and how they depend, for example, on the mass of the final state, the final diffractive state. And you can see some differences between the so-called saturated models and those that don't have saturation, like this shadowing model, this leading twist approach. Okay. There is also other kinds of diffractive processes in which you produce a final state, like a vector meson, and at the EIC, one can do this off large nuclei, also from light nuclei. And there is also some expected difference between the spectra. So here, this T is the square of the transverse momentum of the produced vector meson. So these are exclusive processes in which you don't break up the target. And these, of course, these processes are very interesting because they provide this tomographic picture of your proton or your nucleus. In this case, that's why you see these dips. These are kind of like the Fourier transform of the so-called Wood-Saxon. But the saturation models show some deviations between what you get with saturation and without saturation. But I should mention that there are other models that have multiple scattering that are able to kind of reproduce these features. Now, the energy dependence and the nuclear dependence might be a way to distinguish between the two. And you see here the deviations are larger for the right figure than on the left figure, because here one is probing larger scales. So once you go to very heavy mesons, you're probing the dilute regime, so you're less sensitive to saturated physics. Now, there is also the semi-inclusive measurements. One of them, which has been promising, is this dihadron suppression that is expected to be observed at the EIC. So one compares what happens in the proton DIS and nuclear DIS. This is similar to the observable that I showed you a few slides back. So this suppression was observed at RIC, and a similar mechanism is expected to happen in DIS. And this suppression is and broadening of this distribution happens because this dihadron pair is going to get a momentum imbalance from the nucleus, and that momentum imbalance is of order of the saturation scale. So if the saturation scale is bigger, you get more momentum imbalance, you get a more broadening of this peak. And so here, for example, is very simple model for the Weizsäcker-Williams distribution, which enters this process. And you see that this Weizsäcker-Williams distribution peaks at larger values of KT if for larger values of QS. So if you compare this red with this black curve, you see that they peak at different locations. So the QS is telling you how much transverse momentum, what is the typical transverse momentum of the partons. And this is manifesting in this observable. There are other mechanisms that can lead to this kind of suppression, also at RIC. Like, for example, the Sudakov, and there are other final state effects that can lead to this suppression. So one has to be careful and distinguish them. There is also more subtle measurements, which now study the azimuthal distribution of the momentum imbalance, and they are sensitive to the so-called linearly polarized distribution of the Weizsäcker-Williams. And they have this, they are expected to have this characteristic cosine 2phi modulation when in the presence of linearly polarized gluons. So this here shows you the ratio of linearly polarized to unpolarized, and it obeys some kind of geometric scaling within this model, and it grows as you go to larger values of KT, which is the expected limit of the unintegrated distributions. These observables are also sensitive to effects from soft final state, soft gluon final state radiation, and that has been studied significantly by Feng, for example, and collaborators. So those have to be taken into account when doing this kind of extractions. Okay, so now in the remaining 20 minutes or so, let me tell you about the status of precision computations in the CGC, unless there is any question that you guys might have. Let me take just a few seconds of a break in case anybody has any questions.
I just want to mention that if anybody have any question and you don't want to ask now, you can always leave it in the chat room, chat window.
Okay, so let me move on. And first, before I get to next to leading order corrections, I would like to advertise a little bit this connection between TMDs and CGCs. So the CGC is valid at the small x, at high energies, and the TMD is typically valid, for example, for this Dijet process when the momentum imbalance is small. So it was shown in this landmark paper that both frameworks agree with each other in their common domain of validity. So when the momentum imbalance is very small and when you are at sufficiently small x. And on these past years, it has been realized how to do this in a more general way, in which, in fact, this connection between CGC amplitudes and TMD amplitudes has been shown to hold, at least at leading order. There is an exact correspondence. And for those of you who are a little bit more familiar with this CGC framework, the idea is that these Wilson lines in the so-called Lycon gauge are given by by Wilson lines along the light cone, but they can be related when working in Lorentz gauge to Wilson lines that are on the transverse direction. So you can replace this pair of lines along the light cone to a transverse gauge link. And this might sound a little bit formal, but in fact, this is the most economic way in which one can show how they are connected to TMDs, because in fact, what you do is you expand these expressions. It's just a transverse gauge link, okay? You expand this expression, you expand this exponential, you have something like this. And then if you consider a small dipole, then you have this kind of expression. So this, you can pull out this out of the integral pretty much, if it's sufficiently small, if the dipole, this distance between x and y is sufficiently small. And this, in fact, will give you half of your TMD. So at the level of the amplitude for digits, you have this pair of Wilson lines. Remember, quark anti-quark scattering. When you square this, you will have 4 Wilson lines. And when you square this guy, you will have 2 of these transverse gauge fields, which are related to the Weizsäcker-Williams TMD. So this is how one makes the connection between the two. This was the way in which was first realized just by a derivative expansion of this product, but recently it has been formulated in a more general way. And the value of this is that it allows you to make this intermediate step in the so-called improved TMD framework, which allows you to resume kinematic power corrections. And so the point is that the CGC cross-section contains the results from TMD, but it also resumes these kinematic power corrections, where this KT is the momentum imbalance. So you don't have to put now any restriction on the KT of the digit pair, or in other words, or the dihadron pair. In other words, you don't have to put any restriction on the angle between them. You don't have to look at back-to-back anymore. In principle, this should hold also beyond back-to-back. And it also resumes, so that's for the improved TMD, for if you use this expansion. But if you use the CGC, it also contains these genuine saturation corrections, which are enhanced with QS. This object here, this TMD, contains already information about QS on the Weizsäcker-Williams, but these genuine saturation corrections go beyond that. They cannot be expressed just as a single gluon exchange of the Weizsäcker-Williams. It goes beyond that picture. And just to remind you, at leading order at least, this production of a pair of quark anti-quark will be given by a Haar factor and this Weizsäcker-Williams. And the reason you have a Weizsäcker-Williams in this case is because of the color flow of the final state. Other processes will give you different color flow and will involve different distributions. It depends on the, of course, on the gauge link structure connecting the two different points in the TMD. And all you have to do when you want to resume this kinematic power correction, so if you use this expression instead, you can show that you still have the Weizsäcker-Williams, and the only thing you need to modify is this Haar factor. What will be not accounted for is what I said, these genuine saturation corrections. And we have made some comparisons between the 3 frameworks, TMD, improved TMD, and CGC, and you can see some differences here. We have done this for the differential yield. We have done this for the azimuthal anisotropies of the momentum imbalance, both looking at the elliptic anisotropy and at the quadrangular anisotropy. And we see that there is some differences, especially between the TMD and the ITMD and the CGC. And the ITMD seems to work fairly well as long as the saturation scale is not too large. But it can, as long as the saturation scale is not too large, and as long as the scales involved in the process, like the transverse momentum of the dihadron pair or the virtuality, are not too large. If they are very large, then these genuine saturation corrections, which is scaled as QS, would be suppressed by these Haar factors. But at the EIC, if one wants to probe small x, one shouldn't go to too large of these scales. And so there is hope that these genuine saturations can be accessed at the EIC. Now let me go on the next minutes to discuss the status of next to leading order computations. So the structure functions have been evaluated. In fact, there are fits to Hera data at NLO and next to leading log BK evolution. And they are shown here. And what you notice, perhaps not on this plot, is that already the LO, the leading order results plus leading log evolution provide a good fit to Hera data. So how can we interpret that? If you go, so what's the point of going to NLO, right? The thing is that when you do these fits, there is freedom. There is some parameters which allow you to fit these results. So to really put to test and constrain the CGC is to, one possibility is not just to constrain to Hera data, but look at multiple observables across different colliders and perform a global fit, a simultaneous fit of the data, first at leading order and then at next to leading order, and see if the fit quality is better. If you just look at Hera data, you see that both fits, the LO and NLO fits, are equally good. Perhaps the NLO is slightly better, but the differences won't be so dramatic. So these fits, in principle, one can already play with this next to leading order evaluation of the structure functions in the CGC. It has only been done for light quarks. The massive quarks are still underway. And I hope that we can also see predictions for the EIC, because this has, of course, only been done for Hera data. There is some progress towards exclusive vector meson production at next to leading order. So this requires massive quarks. And only the longitudinal polarization is known. So there is still no comparison with Hera data, because one needs a transversely polarized photon. And in this case, you see that if you constrain the LO fit and the NLO fits, and for the NLO fits, there is different resummation schemes for the BK evolution to next to leading log, you see that there are differences, okay? So here, of course, there is no fit to Hera data. This is just what the results come out from these different fits. And you see that there is some differences already in the JSI production. I think one should be careful, because here one is really probing light quarks. Only the light quark component of the structural functions have been computed. Here one is sensitive to massive quarks, and that might play a role. So now there is also some results for exclusive diet production. Only real corrections have been computed. So these are only partial results, and you can find it in this paper. And different contributions from these real corrections are shown here. And it seems that there is a significant importance of the NLO contributions. I will not go into too much detail, because I'm not extremely familiar with this computation, but I encourage you to look at this paper for more details. And then there is work that we have done recently and put over in the last couple of months with my collaborators at Brookhaven, which is looking at semi-inclusive diets, or in this case diets, but this calculation can be accommodated for dihadrons as well, and next to leading order. And we don't have numerical results yet, because the expressions, these analytic expressions were not known when we began this project. So our goal was to compute them. And in fact, it's not too difficult to begin to do these calculations, but they can get very long and very tedious. And just to give you an idea, there is multiple channels, as you would expect. So you have this quark anti-quark pair, and then you have to dress it in multiple ways. to evaluate the NLO computations. And the fact that you have multiple scattering makes the loop corrections more complicated compared to standard computations in perturbative QCD. But we have managed to show that this process is IRC safe. We have shown that UV divergences cancel without the need to introduce counter terms at this order in perturbation theory. We did this for, of course, light quarks. It would be the dominant component for digits. And we showed that this Jim-Walk factorization. So we show, so if you go back to many slides, we should show you before, when you do these corrections, there will be terms that will be enhanced by high energy logs. And we have managed to show that those satisfy Jim-Walk evolution. And we have isolated the so-called impact factor, which is not enhanced by the rapidity high energy logs. And but still, the expressions are, we hope that can be numerically tractable. That's something that we want to pursue in the next months. We first want to make contact with this back-to-back limit in which we can make a connection with the TMD framework. And we want to study things like Sudakov resumation. So our impact factor in principle should contain a log that is enhanced in the back-to-back limit. And we are trying to make it more manifest from our expression. So even though, as I said, this impact factor is of order alpha S, in different kinematic regimes, it can generate large logs which need to be resummed. The logs that we have resummed so far for general kinematics are these high energy logs, which have been shown to satisfy Jim-Walk evolution. But this computation is necessary to really test what are the size of the expected NLO corrections for this process. And we hope that soon we can obtain numerical results as has been done for the structure functions. Okay, so I see I have 5 minutes left. So let me close with the outlook. I think within the next few years, the so-called CGC TMD correspondence has to be fleshed out, not only at leading order, as has been done, but also at next to leading order. And perhaps it can be extended to understand GPDs and Wigner's distribution. So I didn't touch too much on that, but the CGC is also applicable for diffractive processes, exclusive processes, where the target remains intact. And these processes are of course sensitive to generalized Parton distributions, Wigner distribution. And it has been shown that it has connections with the small x. But typically this is done at leading order, so perhaps there is room to investigate what happens at NLO. We want also predictions for the CGC next to leading order, numerical prediction. Eventually, the goal would be to do some global analysis, including data from HERA, from proton nucleus collisions at RIC and at the LHC, and also ultraperipheral collisions. This has to be done carefully, because some kinematic regimes might develop large logs next to leading order, and those have to be resummed, for example, the Sudakov. And hopefully we can parameterize and constrain more the initial conditions of these Wilson line operators. Because at the moment, what typically is used is the so-called MV model, the McLaren-Venugopalan model, which was conceived for a large nucleus. But as of now, there is some close alternatives, some close extensions to MD, but I think there is room to make parametrizations of other parametrizations that can better describe physics. But of course, this goes in hand with proper fits, and this requires higher precision. So this is how all ties together. And the reason we want to study the CGC TMD correspondence is because the TMD framework has been developed significantly more than the CGC framework. And we hope that we can import the ideas of the TMD and the technology that has been used there to push the CGC to higher precision studies. So that's it. That's what I have for today. Thank you very much for your attention. And now I will take any questions that you may have to the best of my ability.
Well, thank you, Farid, for this talk. So let's see whether we have any questions from the audience. Please just raise your hand, or you can just speak directly.
Maybe I started with a question.
Yeah, go ahead. Yeah.
Farid, if you go back to maybe the previous slide, when you're talking about jet functions. Yeah, right over here. This so you're using this small cone definition. What is? Can you explain what is this ZG, ZJ? Those variables.
Yes. So ZG is the momentum of the gluon.
Inside the core, you mean inside the jet?
Yeah, is the transverse. Sorry, is the longitudinal momentum fraction of the gluon inside the jet.
Okay. What
Yes.
about ZJ?
ZJ. So yeah, in this case we will pair. So we have three partons in the final state: the quark, the antiquark, and the gluon, right?
Mm.
So whether if the quark and the gluon form the jet, then ZJ will be the sum of the longitudinal momentum fraction of the quark and the gluon. If the antiquark and the gluon form the jet, then this ZJ will be the sum of the longitudinal momentum of the antiquark and the gluon.
And there could also be a situation when just a quark form the jet, and then the rest of the quark and gluon become a finite correction.
Right. So there can be a situation, yes, in which the ZG would be just the Z of the quark or the Z of the antiquark.
I see. Okay.
Yes. Yes. And the reason we use this simple small cone condition was a proof of principle that this observable is IRC safe in the CGC. But of course, one should go beyond this simple algorithm, the small cone algorithm. I think for real phenomenology, one has to do better than this. Yeah.
Okay, sounds good. So did you actually connect, trying to study whether your jet definition has any similarity with like typically the jet function people derived from effective field theory framework?
So we have not explored that direction, and that's something actually that I would like to study with you. That's a direction that I think would be interesting, because yeah, typically, as I said, the CGC computations for these more differential observables are a leading order, and what it's naively done is they just couple these partonic results to some kind of event generator, but you see, there is room for improvement for these kind of observables. Yeah. That's definitely something I want to look with you.
Great, great. Okay, that's very good.
There any other questions? Well, while people are thinking, let me ask you for this question. For this slides there, I just want to make sure that what do you mean by dijet? I mean, in a leading order, when you only have the dipole and then dipole scattered with the nuclear, this is not a dijet. This is just a single jet, right? And
it would be a dijet, or you have a quark and antiquark, and each of them.
Yeah, but they are not really dijet, right? I mean, it depends on which frame you're looking at. If you look in a normal, not using dipole picture, just like photon come in and scatter with quark, and then this is one of your diquark essentially become another line coming from the target.
I see what you mean. I think,
and
yes,
yeah, in this case, unless Because
think
where's your target? You know,
I think the way you should think about this process of dipole picture is as a photon-gluon fusion process. You have a gluon. So imagine I expand this shockwave, right, to lowest order. I can replace it by just a single gluon exchange.
Yeah, this is why I trying to clarify with you. So
Yes.
your dipole picture is default is like your photon and glue fusion process.
Yes. So that's why when I let me make yes, maybe this diagram makes it clear. So to lowest order in exchange, this shockwave will contain okay, it actually has both. At leading order, it has both channels of photon-gluon fusion, right? The gluon attached to the quark and the gluon attached to the anti-quark. So there is also this channel, right? So if I expand, maybe I can give a little bit more details. So,
and then if in this picture, what happened to the leading order diagram? Just like photon scattering off a quark.
Right. So then the Compton scattering, the QCD Compton scattering, which will be a quark, right? So I think you're referring to this channel. Right?
No, even not that.
Which one?
Just the photon scattering off a quark.
But how do you get digits?
There's no digit. I mean, that's what I'm saying.
Right.
In that case, there's no digit, right?
Yes, in that case, there is no digit. But if I insist that I want the digit,
very often, I thought that diagram, the leading order diagram, is equivalent to the dipole model.
I don't think so. I also used to think this way, but I think the way you should think about it is really that this shockwave lowest order exchange corresponds to photon-gluon fusion. Let me just draw a diagram to make sure I understand what you mean, right? So you mean this kind of thing?
Yes.
Right, and I guess you may have some.
It will depend on where where the photon come from, where that quark come from. If the quark will from initial state radiation can emit another soft glow, this is equivalent to a dipole. In a dipole picture in a certain kinematic region, right?
Yeah, I'm not sure about that. Because I can show explicitly that really if I expand these Wilson lines, right? So if I have this V as this exponential with path ordering. So if I expand this to lowest order, right, I have 1 minus G, okay, A dx. And so if I have VV dagger minus 1, I have, you're going to have this IGA dx. And then some corrections which come to higher orders. And then this really is the scattering with the gluon. That's how we make the connection with TMDs, right?
Okay, so in this case, I mean, in your language,
right?
This dipole process is not the total cross section. It does not, for the total cross section DIS, you have to also include the leading order. This just photon scattering.
Right.
That's what I would consider. That's the leading term. That's the leading order of DIS.
Yes, but at the small x, that would be suppressed, right? Because the gluons are going to dominate. So I agree with you that this channel in perturbation theory is going to be alpha S suppressed.
Yes, of course. At very small x, yes.
Yes, but
dominated by the glue, yes.
But that's an excellent question because when I say a small x, I'm not telling you exactly how a small x has to be, right? Typically, we make the assumption that sufficiently small x, like this CGC is for sufficiently large energies. So one should study this background, like this channel here, for example, this channel here is going to be a background to our diet process or our diet event, and even at leading order, right? But we expect that channel will be suppressed at the small x kinematics. But quantitatively, one has to include it, right? And see if indeed it's suppressed.
Okay, yeah, I somehow in my mind I thought there is always some kind of equivalence between this dipole model and then the normal DIS, as you know, in a different framework. I mean, essentially it depends on whether you are looking at the rest frame of the target or the infinite momentum frame of the target.
Yeah, I understand where you come from, because I've seen this interpretation as well. And maybe for the total cross section, it's true, but for I don't think this is true for digests. I don't see.
No, not for digest. Definitely for not for digest. And for the digest, I would imagine, you know, this diagram, especially the diagram expanded into a photon glue fusion, is probably the dominant one.
Yes.
Plus, of course, there is this quark scattering with the glue radiation, and which is not necessarily small, especially if the quark is a C quark.
It could not be small, so yeah, it has to be taken into account. I mean, what one could do, best scenario, is to distinguish between gluon jets and quark jets, but maybe this is asking too much, right? And one can see if it comes from photon gluon fusion or the Compton scattering.
Yes. Okay, and I think if there's no further question, I think we are already 10 minutes over past the time.
You know, I know most of you here, so I'm sure you can ask me questions later. So but if anyone, I see also some people that I haven't interacted directly with, so please feel free to send me an email if you have any questions later. I think the slides are going to be posted. So yeah, feel free to contact me.
Okay, well, let's thank Farid again, and so we will see you next week for the hit.
Yeah.